Until recently, spectroscopic observations of the interstellar object 3I/Atlas consistently indicated a reddish coloration, a trait commonly associated with organic-rich dust on the surfaces of icy bodies exposed to cosmic radiation. However, this long-standing interpretation has been challenged by new observational evidence. An image obtained on September 7, 2025, reported by experienced astrophotographers Michael Yeager and Gerald Riemann, shows that the diffuse glow surrounding 3I/Atlas has taken on a distinctly greenish hue. This apparent color transition is not merely aesthetic. It may reflect a fundamental physical and chemical change in the material being released from the object as it travels closer to the Sun. Such a shift invites careful scrutiny because color in cometary comets is often a tracer of specific molecules and emission processes, rather than a simple reflection of sunlight from dust grains. One plausible explanation for this color change is a sharp increase in the production of cyanide CN, as measured by the European Southern Observatory's Very Large Telescope on August 25, 2025. CN is a well-known contributor to green and green-blue emission in cometary comets, and its presence in large quantities can dramatically alter the observed color of the surrounding cloud of gas and dust. What makes this case particularly intriguing is not only the detection of CN, but the reported scaling of its production rate. Both cyanide and atomic nickel were found to increase dramatically as 3I/Atlas approached the Sun, following a steep power law dependence on heliocentric distance of approximately -9, with an uncertainty of about 1 in the exponent. Such an extreme sensitivity to solar distance is highly unusual. Even more puzzling is the detection of nickel without a corresponding abundance of iron, which defies expectations based on typical solar system comet compositions and raises questions about the primordial environment in which this object formed. Additional insight comes from data released by the Atlas Telescope team, covering observations as far back as March 28, 2025. These data reveal that the effective cross-section of scattered light around 3I/Atlas evolved in a complex and non-monotonic way as the object approached the Sun. When the object was farther than about 3 astronomical units, the scattering cross-section increased steeply with decreasing heliocentric distance, following an inverse power law with an index of approximately 3.9. This behavior is consistent with increasing dust production from a surface coated in dark, reddened material, where sunlight liberates dust grains that efficiently scatter light. However, once 3I/Atlas crossed inside this distance threshold, the growth rate slowed dramatically, with the power law index dropping to around 1.2. The Atlas team interprets this break as evidence for a qualitative change in the nature of the material being released, a transition from dust-dominated scattering to the production of small, optically bright icy grains that modify the opacity and radiative properties of the expanding plume. This interpretation is reinforced by high-resolution space-based observations. A Hubble Space Telescope image obtained on July 21, 2025, when 3I/Atlas was at a heliocentric distance of 3.8 Australian dollars, shows an unusual morphology in the distribution of scattered light. Instead of forming a tail that extends away from the Sun, as is typical for comets driven by radiation pressure and the solar wind, the observed extension is oriented toward the Sun. Such a configuration challenges conventional cometary models and suggests that forces other than simple dust blowback are shaping the surrounding material. This sunward extension may point to the dominance of gas drag and isotropic outgassing, or the presence of unusually small grains that respond differently to solar forces. Complementary data from the James Webb Space Telescope, collected on August 6, 2025, and from the SphereX Space Observatory between August 8 and 12, 2025, further complicate the picture. These infrared observations indicate that the gaseous environment around 3I/Atlas is overwhelmingly dominated by carbon dioxide, which accounts for roughly 87% of the gas by mass. Carbon monoxide contributes about 9%, while water vapor makes up most of the remaining 4%. This composition is striking because water ice is typically the dominant volatile in comets originating from the solar system. a CO2-dominated coma, suggests formation in a cold environment with chemical conditions quite different from those that shaped most known comets. When combined with the object's trajectory, which is closely aligned with the ecliptic plane of the solar system, a configuration with an estimated chance probability of only about 0.2%. These compositional anomalies make 3I/Atlas stand out as a particularly unusual interstellar visitor. The contrast between 3I/Atlas and the two previously identified interstellar objects is stark. The first, 1I/Oumuamua, exhibited no clear signs of outgassing, yet displayed a significant non-gravitational acceleration, sparking debates about its shape, composition, and possible mechanisms for propulsion. The second, 2I/Borisov, behaved much more like a conventional comet, with water-rich outgassing and familiar dust dynamics. By comparison, 3I/Atlas seems to occupy a category of its own, chemically exotic, dynamically peculiar, and morphologically inconsistent with standard cometary expectations. While none of these properties alone demands an extraordinary explanation, their combination challenges the assumption that all small interstellar objects can be neatly classified using the same frameworks developed for solar system bodies. Against this astronomical backdrop, discussions closer to Earth about unidentified anomalous phenomena, or UAP, continue to unfold in the political arena. On the same day as these scientific developments, a hearing of the Task Force on the Declassification of Federal Secrets in the U.S. Congress is being chaired by Congresswoman Anna Paulina Luna. Titled Restoring Public Trust Through UAP Transparency and Whistleblower Protection, the hearing features testimony from individuals with military and intelligence backgrounds, including U.S. Air Force veteran Jeffrey Nuxatelli. Notably, the first recommendation in his testimony is to fund independent research and to treat the study of UAP with the same seriousness afforded to any other scientific field. This recommendation aligns directly with the guiding principles of the Galileo Project, which emphasizes systematic data collection, transparency, and rigorous analysis as the only reliable path toward understanding anomalous observations. In a recent interview on News Nation's program Morning in America, following an earlier discussion focused on 3I/Atlas, the question arose whether the release of new videos or eyewitness accounts during the congressional hearing would reignite public interest in UAP. The response emphasized that this is not a matter of public relations or entertainment, but one of substantive importance for both national security and science. Throughout history, humanity has clung to deeply ingrained misconceptions long after contradictory evidence was available. The geocentric model of the universe, which placed Earth at the center, remained widely accepted even though Earth had already completed billions of orbits around the Sun. This historical lesson underscores how social consensus can lag far behind empirical reality. From a scientific perspective, the decisive factor in resolving debates about UAP or about anomalous interstellar objects like 3I/Atlas is credible, high-quality evidence. Once such evidence is available and subjected to open scrutiny, interpretations tend to converge, regardless of prior beliefs. When asked whether governments are concealing information, the appropriate scientific stance is neither blind trust nor reflexive suspicion, but a commitment to follow the evidence wherever it leads. Assertions without data, whether reassuring or alarming, carry little weight compared to measurements that can be independently verified. Ultimately, scientific evidence remains the most reliable pathway to new knowledge, whether the subject is an unusual interstellar visitor or unexplained phenomena observed in Earth's skies. A useful way to distinguish dogmatism from genuine scientific inquiry is to examine how each responds to anomalous data. Dogmatists, committed to preserving established narratives, tend to dismiss or ignore observations that do not fit existing models. Open-minded scientists, by contrast, regard anomalies as opportunities, signals that nature may be revealing something new. This attitude is grounded in humility, an acknowledgement that the universe is often more imaginative than human expectations, and that it operates independently of our conceptual frameworks. Nature does not owe us simple explanations. nor does it adjust itself to our preferred categories. The insistence that everything observed in the sky must be either a familiar icy rock or a product of human technology may offer temporary comfort, but it does not constitute understanding. If cosmic neighbors exist, whether in the form of unfamiliar natural objects or something more exotic, denying the possibility will not make them disappear. Only through careful observation, rigorous analysis, and a willingness to revise our assumptions can we hope to grasp our true place in a universe that continues to surprise us.